Today's lecture 26. We are going to do another optimization problem to start with, maximizing a viewing angle. And we'll make an animation on Mathematica that will hopefully inspire you to do things for your project on Mathematica. We'll go back to that logistic differential equations and its solutions. We'll make graphs of the solutions with and manipulate in Mathematica in a slope field. Something called a slope field is new. Lecture 26b, we'll do more on slope fields, and we'll do a few related rates problems, and we'll try to keep those pretty basic. Your assignment over the weekend will be a little shorter. You might say significantly shorter, actually, than the assignment that was due today. I think it's going to be a pretty cool day today. I think lots of interesting stuff to be thinking about here. So here's a general kind of problem about maximizing a viewing angle. I'm going to assign an even problem over the weekend that this is based on. It's problem number 44 on page 213, section 4.3. It's about maximizing your viewing angle for the Statue of Liberty. And I put the answers on Moodle so you can see what the answers are, but I'm going to go through a more general derivation, again with an eye toward helping you get some extra credit on your project. And this is, again, a more important kind of thing to be able to handle, is dealing with arbitrary parameters in the problem. So the question says, to get the best view of a statue of height h on a pedestal of height p, so h is the height of the statue, p for pedestal is the height of the pedestal, you should stand where your viewing angle is maximized. So you stand back from the statue and you're looking at it. You want the statue to look as big as possible in terms of your viewing angle from your eyes. For the sake of simplicity, let's not worry about your height. So let's assume you are on the ground, on your stomach, and you're taking a picture of the statue from there. Okay, so we don't have to worry about your height. The question is, how far from the base of the statue should you be? Let's draw a diagram over here on the right side of the board of the situation. Now you can try to actually make a little bit of a pedestal if you want. And you can try to make it like a little drawing of a statue if you want. Okay? Very, very, very bad drawing of a statue there. Maybe it looks like a character from VeggieTales or something, right? That's like Larry the Cucumber or something. And you're going to be over here on your stomach looking at this statue. Your viewing angle is not for the pedestal, just for the statue. So if you draw a line between your location and the top of the pedestal, which is the bottom of the statue, and then another line from your location to the top of the statue, that's the angle that you want to maximize, make as big as possible. In terms of what independent variable? In terms of your horizontal distance to the statue, say the middle of the statue, right here, call that distance, how about x? We want to maximize theta as a function of x. That's our objective function. Maximize theta as some function of x. In terms of two parameters, h and p. H is the height of the statue, that's this distance right there. P is the height of the pedestal. For the Statue of Liberty, if I remember correctly, the book tells you that P is 46 meters and H is 92 meters, so that the Statue of Liberty is twice as tall as its pedestal, which seems kind of surprising. You probably didn't realize its pedestal was so high compared to the overall height. The pedestal is 1/3 of the overall height there. That's if we're trusting the book at least. Okay? So if I'm going to use subscript notation, I don't have to, but if I'm going to, I can put an F sub h comma p, or in fact, if I'm going to program this in Mathematica, which I'm going to do, I would want to have subscripts like that. I've got a family of functions, one function for each pair of numbers, h and p. Any idea about what to use here to help us figure out what the formula for this function is? What kind of mathematical subject would be helpful, do you think? This is a right triangle there. There's also a big, oops, over here one. There's also a big right triangle. Pythagorean theorem, you think? Yes, no? We are talking about an angle. Oh boy. What's everybody's least favorite math subject? Don't say calculus. Trigonometry. Oh, I'm sad that's your least favorite. It's one of my favorites. Just kidding. Well, okay. It's not my favorite, but I do enjoy it. Got an angle. This angle, though, is not a part of a right triangle. Yikes. That sounds difficult. We're always so used to right triangles. There is something called the law of cosines that might be useful, but something better, though, is to think of this angle theta as the difference of two angles in the two right triangles. Call this big angle, say, alpha, and the smaller angle, beta. Theta equals alpha minus beta. Alpha of x minus beta of x. And both of those depend on h and p as well, perhaps. I won't bother with the subscripts. What do you think? Sine, cosine, tangent? What would be most helpful? SOHCAHTOA. Don't misspell them. I've got some opposite sides over there to the angle. I guess I have an adjacent side. I don't have the hypotenuse, though I could figure it out. It's probably easier to use tangent, though. TOA, right? T-O-A. Tangent is opposite over adjacent. So for alpha, the opposite side is h plus p, and the adjacent side is x. And for beta, the smaller triangle, the opposite side is p, and the adjacent side is x. And I'm solving for the angle, so I need to use the inverse tangent. Uh-oh, this looks complicated. Inverse tangent for alpha, the big one, opposite is h plus p, adjacent is x. For beta, it's an angle as well. Opposite side is p, adjacent side is x. I guess this is the function we have to maximize. Let's do it all in Mathematica. Well, let's do it by hand first on a slide here. Then we'll put it in Mathematica, and let's make a Mathematica animation to visualize it. And the things I do, you'll want to take note of because they could be very helpful for your project. But here's a quick solution. Maybe don't write this down because I'm going to go kind of fast, okay? Just look at it and say, nod your head and say, yeah, if I had to, I could do it. If my life was on the line, I could take those derivatives and stuff. I might feel really scared, but I could do it if I had to. Based on my drawing on the board, we already know this, okay? There's alpha of x, there's beta of x. We're subtracting to get theta as a function of x. That's my function I want to maximize. So I've got to take its derivative and set it equal to 0 to find the critical point, right? There's the derivative. Yay! Whoa, isn't that beautiful? What did I use? I used the derivative of inverse tangent, for one thing. The derivative of inverse tangent of x, recall, from the gateway, which most of you have passed now, but some of you still need to pass, is 1 over 1 plus x squared. Oh, but I don't have plain x's in here. I've got things over x. I've got to use the chain rule too. So in each case, like with this one, I get a 1 over 1 plus the inside function squared, the h plus p over x quantity squared. The chain rule says now multiply times the derivative of that thing, which is, by the way, the same as h plus p times x to the negative 1 power. So an h plus p is just a constant when I do the derivative, at least. So I get negative h plus p times x to the negative 2 power. You see the negative sign there? You see it dividing by x to the positive 2 power. A similar kind of thing happens with this one. Very similar. But now I can simplify those things. I can bring the negative signs out in front, and these two negative signs here and here cancel. I can also bring the h plus p up top and the p up top there. I can multiply the bottom here by x squared there and there to get that. 1 times x squared is x squared, and then x squared times this, the x squareds cancel, leaving me with h plus p quantity squared. Similar kind of thing here, x squared times 1 is x squared, x squared times this, the x squared is canceled, leaving me with a p squared. So it simplifies a little bit. Set that equal to 0 and solve for x. Two fractions on one side. Maybe I should get one of the fractions on the other side and cross multiply, like I did the other day. Or I could get a common denominator. It sounds like it would be easier to cross multiply after I rearrange. I mean, I could multiply by both of these denominators at the start anyway, but I think it's probably easier to think about it this way. So there I've got rearranged it. My goal is to solve for x. Cross multiply. You got a p times x squared and a p times this thing. That's what you see here. Equals, cross multiply these two. X squared times h plus p is hx squared plus px squared. And then p squared times h plus p is hp squared plus p cubed. Okay, it looks a little bit better. Now I want to continue trying to simplify. I probably should expand this with FOIL. H squared plus 2hp plus p squared, and then multiply everything times p. And I'm going to do a little rearranging. My goal is to solve for x. The p times x squared is here and here cancel, right? If you subtract p times x squared from both sides, they both cancel. They both go away. That's good. The only thing that involves an x is just that. That's good. I put it on one side and I put everything else on the other side with appropriate signs if you are careful. And stuff cancels more. P cubes cancel. And this partially cancels with that. It simplifies to that. Now divide by h and take a square root. Right? Solving for x. I don't need the quadratic formula because I got x squared on one side, then there's no other x's. I don't need the quadratic formula. I can just divide by h and take the square root. That's what I did. Divide this by h, you get h. Divide this by h, the h goes away. ph plus p squared. Take the square root. There's your critical point in terms of h and p. For your statute of liberty problem, you could just plug in p equals 46 and h equals 92 and you'd be done if you're just relying on what I did, but you should re-go through the process. Right? Without peeking. Okay? You're going to learn more if you re-go through the process. You've got particular numbers. But if you plug those in here, you'll get the right critical point, the right distance. And I'm going on memory here. I think for the Statute of Liberty, the critical point ends up being 70-something meters. Okay? That's what it ends up being. What's the actual maximum angle? And is it a maximum? We've always been minimizing so far. Is this one really going to be maximized? You have to plug the critical point into the function. It's very complicated. Okay? Very complicated formula for the actual maximum angle. I don't want to look at that too much. Let's go to Mathematica, and let's do this problem in Mathematica now. Okay, let's get the function in. So you're going to be doing this kind of thing for your project. Put the function in. Since it's a function of x, I want x to be the main variable. But since I have parameters, I probably want a subscript. I can use this button over here in the Basic Math Assistant, which you can get to through the Palettes menu, Basic Math Assistant. That gives me subscripts. I can go f sub h comma p. I need underscores after the h and the p. Tab over of x underscore. I am thinking of h and p as being constants, but they could change ultimately if I make an animation, so Mathematica needs to be programmed to think of them as variables, and so I need underscores when I first define it. Don't use the underscores after that. Mathematica doesn't do inverse tangent, it does arctangent. Capital A, capital T. Looking at the formula over on the board, maybe with the video camera, you want to look again over at the formula on the right here. On the lower right, again. This is the alpha of x here. And now the beta of x, I'm subtracting. Okay, so compare this with this over here. It's the same function. I just typed it in. Arctangent means inverse tangent. Am I really going to get a maximum? Let's do that first. At least with the statute of liberty. I could use the second derivative test. But let's go ahead and plug in the height of 92 for the statue and 46 for the pedestal. And graph this as a function of x. X is a distance, and I said when I did the calculation it was maximized when x was around 70 something. So let's let x go to at least 80, maybe 100 here. There's the graph. I'll go past 100. You'll see it change even more. I'll say to 500. That's theta as a function of x. You can see it's maximized when x is around, yeah, maybe 70 something. We can have Mathematica do the calculations for us. Well, we can do the derivative. When you use the subscripts like this, you can avoid the d. You can just use a prime. Tab over to a prime right there. There's the derivative. We can simplify it. We can solve for when the derivative equals 0. Just put the copy and paste this in here. Do double equal signs. Remember to do double equal signs. When is that derivative equal to 0? Oops, let's see. That's a mistake. Comma x. There we go. That is the same. This is a negative x. We want x to be positive, so we use this one here. That is the same as the answer I got before. It just separated the square roots into two pieces. It is the same as this thing. Factored out a p and separated the square roots into two square roots. It is the same thing. Is it really a maximum? Certainly the graph makes it seem that way. We can try to use the second derivative test. Is the second derivative always negative? Actually, it's not. You can see from the graph. It's concave down here, so it's negative here, but it looks like it's positive over there. So if I try to do the second derivative symbolically here, it will not be clear whether it's positive or negative, because it depends on what x is. Yikes. But I could try plugging that critical point into the second derivative and see if it simplifies nicely to something that's obviously negative. Yeah, it did. How about that? The power of Mathematica here. Just having Mathematica do the calculations for me in the natural way. Make sure you use square brackets for the inputs. Just copy and paste, plug them in, simplify. That's clearly negative for this value of x, that critical. Yeah, everything else inside besides that negative sign is positive. Cool. That means at the critical point, the graph is concave down, you've got a max, a local max. Could the graph possibly go back up again? It won't, though in theory it could. In general. It won't for this example. It'll definitely keep going down. But it is concave up over there, so the second derivative is not always negative. It can be positive. It's only negative at the critical point. We could put this inside of manipulate to change h and p if we like. Let's go ahead and start with the values for the Statute of Liberty. The height is 92. If I let that also get smaller or larger, I might do something like this. That'll let h go from 50 to 200, starting at 92. And for the pedestal, I started at 46 and let it go down to maybe 10 and go as high as 50, say. And probably to make the graph nice, I need to keep a fixed plot range here. Oh, say 0 to 500 for x, like the one above. And what is theta? Theta is an angle in radians, by the way. That's an angle in radians for the vertical axis. Pi over 2 is 90 degrees. That would not do. That would be about 1.57 radians. It doesn't go higher than that for sure. I could go 0 to 2. It's for sure not going to get higher than that, no matter what h and p are. And I can see how that maximum point changes as h and p change. That's pretty interesting. As p gets real small, as the pedestal gets real short, the maximal viewing angle gets larger, and you've got to be closer to the statue. If the statue's pretty much right on the ground, you got to be pretty close to it to have a maximal viewing angle. On the other hand, when p is large, the maximal viewing, so the pedestal's real high, the maximal viewing angle is smaller, and you got to be pretty far away from the pedestal to get that maximal viewing angle. Now let's also spend a few minutes trying to make some other kind of animation where maybe we can play with the values of h and p and see visually how the statue and the angle changes. Remember last time I showed you about graphics and graphics 3D. We made an interactive cylinder. Here let's keep it two-dimensional. Good question? No? Okay. Here let's keep it two-dimensional. So instead of using graphics 3D, we'll use just graphics. Let's make some lines in a diagram, like the lines you see on the board here, these lines. Let's see if we can get those in the diagram and let them change as h and p change. So you can see that angle in there. How do you do that? Well, I like making my lines thick, so I'm going to put the word thick in there, with capital T. Oh, let's make the one that's on the ground, let's make it black, so put the word black in there. Separate these things by commas. Line makes lines. How about that? What's the syntax of what goes in here? Say we want to say you are at the origin, and we want to go out to say 75, 0 for the end of this line. That's the way you do it. This will make a line starting at the origin 0, 0, and going out to the point 75, 0, like that. Now you can't see the axes, so how do you know that's 75, 0? We can add in axes. We can go axes, arrow, true. And there we have some axes. We could, I want to change this, maybe how big x is. So I probably want a bigger plot range. Inside, after the axis is true, I can do a plot range. Say 0 to 200 in the x direction and 0 to 200 in the y direction. The vertical direction is not an angle anymore because we're looking at the picture of the statue. And maybe make my picture smaller. I can do that by zooming out here. Let's put this inside and manipulate. And change the right endpoint. Change the value of x. This is similar syntax to what I did before. X comma, start at 75, let it get smaller, maybe down to 20, and get bigger if you need to, up to 200 or something, or maybe 150. And I also need to change that 75 to just an x. That'll change, allow me to change the line. It goes from the point 0, 0 now to the point x0. You move the slider, you can change that line. Change how far you are from the base of the statue. How about the other lines in here? Well, we could do another line. And here we could put a comma. Maybe we change a different color. Maybe blue for the, this is going to be the pedestal. I'm not going to literally draw the pedestal. That would take too much work. But coming back to this picture, I'm going to draw this line segment right here. Get this picture here in the camera. And draw that line segment right there. Where does that line segment start? It starts at this point. X comma 0 and goes up to x comma p, I guess. I guess I'm going to have to animate with p as well. X comma 0 and then x comma p, but Mathematica needs to know what p does. I'm going to put it in there. The height of the pedestal. Change this x to a p. The one from the book that starts out at, say, 46 meters. Let it go down to, say, 5 and as high as 50. this now allows me to change the height of the pedestal as well. I can change the height of the pedestal. I can change my distance to the pedestal. Mathematica often is about just mimicking. You just got to mimic what I do. Don't worry about why it works. It's programmed to work. You got to use curly braces and commas in the way that I'm doing. Let's do another one that goes from, that's for the statute. Come over here, this line here. What are the coordinates of the lower point? X comma P. What are the coordinates of the upper point? X comma H. No, not X comma H. X comma P plus H. The coordinates of that upper point there. So I've got, say, X comma P to X comma P plus H, but I also need to tell Mathematica about H. Let's cut the talking, okay? You guys? I do hear it is distracting. Something like that. Now I've got the statue in there as well that I can change the height of. And now I can also draw lines for the viewing angle. Say from the origin to the bottom of the statue. Maybe let's make that blue. Let's just copy and paste this line with a comma right here. Change this X to 0 so you go from the origin. Now you see a blue line in there. Going from the origin to the top of the pedestal, which is the bottom of the statue. And finally, let's do one that's another red one. This will be our last one here. Starting at the origin, 0, 0, and going to the top of the statue. So now we can see the situation. We can let the pedestal and statue change height if we like, and we can change our distance. And for given fixed P and fixed H, there's some distance that makes the angle here as big as possible. That's the viewing angle. That's the theta. Okay? So I know I went fast. It's hard to digest something in Mathematica, especially going that fast. You can watch the video this weekend if you want more inspiration or you want to be reminded how to do things, but I will save this in the course folder as well. Okay? Let's go back now to differential equations. Look at this slide again, although I've got different things in this slide from last time. And after we go over this slide, we'll take our break. Last time on Wednesday, we talked about a logistic growth model. So we're talking more about differential equations. Today, we're also going to start talking about something called related rates. One of the projects, it's the Saving Lunar Station Alpha, I think, is related to related rates. And related rates kind of has a similar feel as differential equations. It is different, though. The population P, again, will often grow exponentially when it's small, when there's plenty of room to grow. If it gets too large, overcrowding can become an issue, so it can slow the growth. Maybe there's some carrying capacity to the environment. That doesn't mean it's easy to figure out what the carrying capacity is. It's just something that you could hypothesize exists, and I think on Monday, I will try to figure out the carrying capacity for the United States. Could do it for the whole world too, based on population data that's out there. So I will try to do some data science by next Monday and model the population of the US and see if I can figure out its carrying capacity. Not that that's absolutely set in stone, but anyway. Here is the logistic model. This is the differential equation I wrote down last time. dP dt, the rate of change of the population with respect to time, is some constant k, a positive constant, times p times 1 minus t over L. L is also some positive constant. L is the carrying capacity. L for limit because the solutions will approach that as a limit as t goes to infinity. K is kind of like the continuous growth rate, at least when the population is small, because when p is close to 0, this thing is close to 1 and essentially acts like an exponential growth model when p is small. So k is essentially the growth rate, maybe 0.02 or something for 2% when p is small. But when p gets close to L, this gets close to 1, so this difference gets close to 0, and the whole derivative gets close to 0. The slope of the solutions have to go towards 0. You need to be able to think that way when you look at that kind of equation. That's the key to understanding what's going on. As far as solving this differential equation, in Calculus 1, we just don't have the tools. In Calculus 2, if you're going to be in Calc 2, we have the tools to solve this differential equation if we didn't know the answer. But we trusted Mathematica on Wednesday, and for initial population P0, we got this formula initially. Although I think in Mathematica, I actually had either the positive KT here and here, 1 there. But it's more traditional to write it this way. It's also somewhat more traditional to write it this way, though you can't write it that way when P0 is 0. To get from here to here, just divide everything by P0. When you divide that by P0, it cancels to give you an L. When you divide this by P0, it cancels to give you a 1. And when you divide this by P0, well, you just get the P0 on the bottom. And if you let this entire fraction right here in front of the e to the negative kt be called a, then it matches what the book writes in section 4.4. So a, in the book's description of this, is this quantity right here where L is the carrying capacity and P0 is the initial population. Is this really going to solve the differential equation? Well, first it's got to satisfy the initial condition. P of 0 better be 0, or phi of 0 if I'm calling the function name phi. Better be P0. And if you plug in t equals 0, it's simplified to P0. Plug in t equals 0 right there. E to the 0 is 1. This becomes a 1. You get P0 plus L minus P0 times 1, which is this. The P0s cancel there to give you this. And now the L's cancel to give you that. So it does satisfy the initial condition. Let's do the next slide quickly as well before break. The next slide, probably not worth writing down, but just look at it and think about what I'm saying and say, yeah, if I had to, I could check that if I was forced to, okay? When I say that, I mean given enough time, okay? Not necessarily during the time pressure of an exam, right? Because there's too much anxiety for something this complicated. Oh, here's another comment. This definitely goes toward L as t goes to infinity, because as t goes to infinity, an exponential decay goes towards 0. It's 0. So this definitely has a limit of L as t goes to infinity, as long as P0 is not 0. Which it wouldn't be, because otherwise you wouldn't have a population. All right, so here's a slide. Don't write this down. Checking that it's a solution. Just to understand the principle here, you already had a few problems where you were using this principle. You need to take the function and plug it in the left-hand side of the equation, simplify. Plug it in the right-hand side of the differential equation and simplify, and see if you get the same thing. On Wednesday we did with an example, and I put a happy face, right? Because I was glad they were the same. That happens too in this case, but it's more complicated. But just look at this and say, I believe I could do this if I had to. I'm writing it in terms of the book's form, L over 1 plus a e to the negative kt, because it's a bit simpler. To differentiate that, you need the quotient rule. That's the quotient rule. Low d high minus high d low, the square root's below. And you guys have improved a lot in your differentiation skills. From your quizzes to your first gateway attempt to some people's second gateway attempt, you've all done much better with your differentiation over time. You could do that if you had to. T is the variable. Simplify, that's a 0. You can, the two negative signs give you a plus. You can bring the k out in front, which I did for a certain reason. That will become clear in a second here. That's what the right-hand side, excuse me, that's a typo. That's the left-hand side, that should be LHS. I can't change it right now, but that's an LHS. That's the left-hand side of the differential equation. What about the right-hand side? I got that mixed up. That should be RHS. The right-hand side is this. How do you simplify that? You replace p with the function. P P is a function of T. Replace it with the function. So do K times phi of T times 1 minus phi of T over L. Plug it in and simplify. It's essentially, I need to subtract these fractions here by getting, well, let's see. I did cancel the L here. And divide this by L. The L's cancel. Leaving me with 1 over 1 plus A e to the negative kt. That's where this minus 1 comes from because I'm subtracting it. And this part over this is just the same form of 1. That's the 1 there. Simplify, the 1's cancel. Combine the fractions into 1, and you get a match. It does solve the differential equation. Okay, we have a match, it works. Let's end right there for the part A.